afternoon, children. I happily welcome to this online chemistry class. And this morning we studied about Unit 6, gaseous state. In that gaseous state, we studied about the gas equation, that is PV is equal to nRT. Then Graham's law of diffusion and effusion, based on that how to find out the molecular mass of an unknown gas. Now we are going to see the compressibility factor, van der Waals equation, then pressure correction, volume correction, and Andrews isotherm. And there are two types of gases which is called as real gas and ideal gas. The gases which obey the Boyle's law and Charles law are called as ideal gases, and those are all obey the gas equation. But some of them are not obeying those rules. Those are called as real gases. And for real gases, van der Waals gives a new equation that is called van der Waals equation. Before going to the van der Waals equation, he gave some correction in the pressure of the gas, and he gave some correction in the volume of the gases, as well as he is giving one ratio PV by nRT, that is called as compressibility factor. Then after that, we are going to see the Andrews isotherm, that is at which temperature the gases are liquefied and what are the conditions needed for that by means of the graph that is given under Andrews isotherm. Now we are going to see the van der Waals equation in detail.
See the mixture of gases in detail. Studies of the non-reactive gases mixture show that in a gas mixture each component behaves independently. For a gaseous mixture, it is important to know how pressure of the individual component contributes to the total pressure of gas. John Dalton states that the total pressure of a mixture of non-reactive gases is the sum of non-reactive gases is the pressure of the non-reactive gases, the sum of the partial pressure of the gases present in the mixture. And the partial pressure of component gases, the pressure that it would exert if it were present alone in the same volume and temperature. This is known as Dalton's law of partial pressure. That is, for a mixture containing three gases, 1, 2, and 3, with partial pressure P1, P2, and P3 in a container with a volume V, the total pressure P total will be given by P total is equal to P1 plus P2 plus P3. Assuming that the gases behaves ideally, then according to the gas law, P1 is equal to N1 RT by P, P2 is equal to P3 is equal to N3 RT by P. So P total is equal to N1 RT by B plus N2 RT by B plus N3 RT by B. If you are taking the RT by B, the common term out, then you will get RT by B into N1 plus N2 plus N3. P total is equal to N total R by into RT by B. The partial pressure can also be expressed RT by B, that can be expressed as P1 by N1 or P2 by N2 or P3 by N3. Or in general Pn by Nn. Therefore, P total is equal to N total. P1 by N1 is equal to N real divided by N P1. That is, P1 is equal to N by N real, and P total is equal to X1 into P total. That is, we can make it as a first equation. When X is the mole fraction of the ith component. Now we can use the applications of the Dalton's law. In a reaction involving the collection of gas by downward displacement of water, the pressure of the dry vapor collected can be calculated by using the Dalton's law. That is, P dry gas collected is equal to P total minus P water vapor. P water vapor is generally referred as aqueous tension, and its value are available for air at various temperatures. Now let us understand the Dalton's law by solving this problem. A mixture of gases containing 4.76 volume of neon, 0.74 mole of argon, 2.5 mole of xenon. Calculate the partial pressure of the gases. If the total pressure is 2 atmosphere at a fixed temperature. And how to solve this? You can use the formula P neon is equal to X neon and P total. X neon is equal to N divided by N neon, N argon and N xenon. So we will get 4.76 divided by 4.76 plus 0.74 plus 2.5, which is equal to 0.595. Like the same, we are calculating the argon also. N argon divided by N neon plus N argon plus N xenon. That is 0.74 divided by 4.76 plus 0.74 plus 2.5, you will get 0.093. Like the same, we are going to find out the xenon also by using the formula N xenon divided by N neon plus N argon plus N xenon. So you will get the X is 3.312. So the pressure of neon is equal to X neon. Total pressure, which is equal to 0.95 into total pressure is given in the formula as 2 volume. If you are multiplying by 2, you will get 1.19 atmosphere. Like the same for argon, X argon and P total, if you are multiplying 0.093 into 2, you will get 0.186, and for xenon you will get 0.624. And here evaluate yourself. One problem is given. You can try that problem by the same method. Next one is Graham's law of diffusion. Gases have a tendency to occupy all the available space. When two non-reactive gases are allowed to mix, the gas molecules migrate from one region of higher concentration to a region of lower concentration. This property of gas, which involves the movement of the gas molecules through another gas, is called as diffusion. Effusion is another process in which the gas escapes from a container through a very small hole. The rate of diffusion or effusion is inversely proportional to the square root of its molar mass. This statement is called as Graham's law of diffusion or effusion. Mathematically, rate of diffusion is proportional to 1 by root m. Otherwise, Ra by Rb is equal to root of Mb by Ma. When diffusing gases are at different pressures like a Pa and Pb, then Ra by Rb is equal to Pa by Pb into root of Mb by Ma. Here the Ra and Rb are the rate of diffusion of A and B. Ma and Mb are their respective molar masses. Then here Graham's law, one unknown gas diffuses a rate of 0.5 times that of nitrogen at the same temperature and pressure. Calculate the molar mass of the unknown gas. One problem is given. Solution by using the formula rate of the unknown gas divided by rate of nitrogen is equal to root of molar mass of nitrogen by molar mass of unknown. That is 0.5 is equal to root of 28 gram per mole divided by m. If you are squaring both sides, you will get 0.5 the whole square is equal to 28 gram per mole by m unknown. If you are taking m unknown alone, m unknown is equal to 28 by 0.25, which is equal to 112, that is 105 gram per mole. The same one more problem is given, and also the molar mass of bromine is also given. You try the same thing in your chemistry notebook. Next, deviation from the ideal gas behavior. The kinetic energy of gases, that is postulates of kinetic theory of gases, are described in physics textbook, which is the basis of for the gas equation PV is equal to nRT. Assumes that individual gas molecules occupy negligible volume when compared to the total volume of the gas, and there is no attractive force between the gas molecules. Gases whose behavior is consistent with these assumptions under all the conditions are called ideal gases. But in practice, both these assumptions are not valid under all conditions. For example, the fact that gases can be liquefied shows that the attractive force exists among the molecules. Hence, there is no gas which behaves ideally under all conditions. The non-ideal gas are called as real gases. The real gases tend to approach the ideal behavior under certain conditions. Next, an important term we are going to see, that is compressibility factor. The deviation of the real gas from the ideal behavior is measured in terms of the ratio PV to nRT. This is termed as compressibility factor. Mathematically, Z is equal to PV by nRT. For ideal gases, PV is equal to nRT. Hence, the compressibility factor Z is equal to 1 at all temperature and pressure. For these gases, the plot of Z versus P should be a straight line parallel to the pressure axis. When a gas deviates from the ideal behavior, its Z value deviates from unity. For all gases at very low pressure and at very high temperatures, the compressibility factor approaches unity and they tend to behave ideally. The plot of the compressibility factor versus pressure for some common gases are given here in this diagram in the form of graph. First one is the plot of compressibility factor Z in the x-axis and the pressure in the y-axis. Some common gases plot is a graph is given, and in the next one we have the compressibility factor against the pressure. When the pressure is low, the volume of the container is very large compared to the volume of the gas molecules, so that individual volume of all gases can be neglected. In addition, the molecules in a gas are far apart and attractive forces are negligible. As the pressure increases, the density of the gas is also increases, and the molecules are much closer to one another. Hence, the intermolecular force between the becomes significant enough to affect the motion of the molecules, and the gas will not behave ideally. At high temperature, the average kinetic energy of the molecule is very high, and hence intermolecular attraction will become significant. As the temperature decreases, the average kinetic energy of the molecule also decreases. Hence, the molecular attraction is enhanced. The temperature at which a real gas-based ideal gas have over an appreciable range of pressure, that is called Boyle's pressure or boil point. The boil point varies with the nature of the gas. Above the boil point for real gases, Z, that is compressibility factor, is greater than 1. That is, the real gases shows positive deviation below the boil point. The real gases first show a decrease for Z, reaches a minimum and then increases with the increase in pressure. So it is clear that the real gases first show decrease and it decreases. So it is clear at low pressure and at high temperature, the real gases gives us ideal gases. Compressibility factor or a real gas. The compressibility factor Z for a real gas can be written as Z is equal to PV by nRT, and we can write V as a real. V ideal is equal to nRT by P. Substituting this value, V value, in the above equation, then we will get Z is equal to V real by V ideal. Here V real is the molar volume of the real gas and V ideal is the molar volume of the gas which behaves as ideally. Van der Waals equation. J.D. van der Waals made the first mathematical analysis of the real gases, and his experimental treatment provides us an interpretation of real gas behavior at the molecular level. He modified the ideal gas PV is equal to nRT by introducing two correction factors, namely pressure correction and volume correction. Pressure correction. The pressure of a gas is directly proportional to the force created by the bombardment of the molecule on the walls of the container. The speed of a molecule moving towards the wall of the container is reduced by the attractive forces exerted by its neighbors. Hence, the assured gas pressure is lower than the ideal pressure of the gas. Hence, van der Waals introduced a correction term to this effect. Van der Waals found out that the force of attraction experienced by a molecule near the wall are directly proportional to the square of the density of the gas. That is, P is equal to rho square, where rho is N by V. Here, rho is nothing but the density of the gas. When N is the number of the moles of the gas, V is the volume of the container, which is equal to P dash proportional to N square by V square, or P dash is equal to A into N square by V square. Here A is the proportionality constant and it depends upon the nature of the gas. Therefore, P real is equal to P plus A N square by V square. Next, volume correction. As every individual molecule of a gas occupies a certain volume, the actual volume is less than the volume of the container. V. Van der Waals introduced a correction factor V to this effect. Let us calculate the correction term by considering the molecules as spheres. Here it is given, two molecules are given. V is the excluded volume. The excluded volume for two molecules is equal to 4 by 3 pi 2r W cube. If you are considering the pi r W cube, then you will get 8 into 4 by 3 pi r cube, which is equal to 8 Vm, where Vm is the volume of a single molecule. The excluded volume for a single molecule is equal to 8 Vm by 2, which is equal to 4 Vm. The excluded volume for n molecules is n into 4 Vm, which is equal to Nv, where V is the van der Waals constant. And the value of the constant is 4 Vm. V0 is equal to Nv and V ideal is equal to V minus Nv. Replacing the corrected pressure and volume in the ideal gas equation, PV is equal to nRT, we get the van der Waals equation as given, that is P plus A N square by V square into V minus Nv is equal to nRT. The constant A and V are called as van der Waals constant and their values vary with the nature of the gas. It is an approximate formula for the non-ideal gas. And pressure volume isotherm of carbon dioxide. Andrew's isotherm. Thomas Andrew gave a first complete data on the pressure volume temperature of a substance in the gaseous and the liquid stage. He plotted isotherms of the carbon dioxide at different temperatures, which is given in the picture. From the plots, we can interpret some of the factors. At low temperature, isotherms, for example, at the 30 degrees centigrade, as the pressure increases, the volume decreases along AB is a gas until the point B is reached. At B, a liquid separates along the line BC. Both the liquid and the gas coexist and the pressure remains constant. At C, the gas is completely converted into liquid. If the pressure is higher than at C, only the liquid is compressed. So, there is no significant change in the volume. The successive isotherms shows similar trend in the shorter flat region. That is, the volume range in which the liquid and gas coexist becomes shorter. At the temperature of 31.1 degrees centigrade, the length of the shorter portion is reduced to 0 at a point P. In other words, the carbon dioxide gas is liquefied completely at this point. This temperature is known as the liquefaction temperature or the critical temperature of carbon dioxide. At this point, the pressure is 73 atmosphere. Above this temperature, carbon dioxide remains as a gas with all pressure values. It is then proved that many real gases behave in a similar manner like carbon dioxide. Then we will see the other one. Though the nature of the isotherm remains similar, the critical temperature of the corresponding pressure and volume are the characteristic of a particular gas. Now we can define the critical constant as follows. That is, critical temperature Tc of a gas is defined as the temperature above which it cannot be liquefied even at high pressure. Critical pressure of a gas is defined as the minimum pressure required to liquefy 1 mole of a gas at its critical temperature. Critical volume is defined as the volume occupied by 1 mole of a gas at its critical temperature and critical pressure. The critical constant of some of the values, critical constant of some common gases are given in this following table. Okay. Then evaluate yourself is given. Here critical temperature of hydrogen, ammonia and carbon dioxide are given, and we can when we start cooling for a temperature of 700 Kelvin, which will liquefy first and which will liquefy finally. And using this formula, you can find out the answer for this. And the deviation, some of the deviation, the critical constants of the van der Waals are there that we can see in our next class. Now we can conclude ours. This we will see in the next class. Okay. Thank you, children.